Hi, this video explains the maximum likelihood hypothesis for given data. Under certain assumptions, any learning algorithm that minimizing the squared error between the hypothesis predictions and training data that results the maximum likelihood hypothesis. That means when you are having the actual output and predicted output. So when you are having the difference between these two outputs is minimum value, so that will be done by using the squared error, using mean squared error or least squared error, right? So then that learning algorithm is called a good learning algorithm. That result, the minimized result, is called maximum likelihood hypothesis. So here this is the actual output hypothesis, right? This is the hypothesis. This hypothesis uh, uh, given compared with the predicted output from given features, right? If predicted output is close to this hypothesis, that is called, that will have only minimum error, then that hypothesis, this hypothesis is called maximum likelihood hypothesis. So this is find out by using the Bayesian algorithm. The maximum likelihood hypothesis minimizes the sum of the squared errors between observed training values. That means actual output of given training sample and predicted output of the training sample. Assume the observed training values di are generated by addition of random noise. That means the data samples are having noise, right, to the true target value. Here the random noise is drawn independently for each sample. That means the noise is added to the training samples based upon the normal distribution with zero mean. So this is the assumption for given problem statement. So here the learner L considers the input data set and hypothesis space H. Both are having real valued functions which are defined over the given data sample space capital X. That is, each hypothesis in the hypothesis space is function of the form hypothesis is derived from the given input data set. That input data set is tends to R. R represent the set of real numbers. The input data set is having the set of real numbers. For example, our data set may have like this. So in this we are having the features x1, x2, and here actual output label. This is the actual output label. Okay, actual output label. So here the data samples are having real value means float values. Okay, real values. The label will be either yes or no. So 0.2, 0.1, no. So here the this is the input data set capital X. This X is having two samples. Okay, one, two samples. The hypothesis, this is the hypothesis we are given in the data set. This is the H0, right, for the sample 1. This is the H0 for sample 2, right? That is the explanation for this statement. The problem faced by learner L is to learn unknown target function, right? That is represented with F. So we are going to uh, calculate the hypothesis for unknown target function. If there is, that is drawn from the hypothesis space capital H. If there is m number of training samples, the target value for each training sample is corrupted by random noise, which is drawn according to the normal probability distribution. That's the so due to having our data noise, our data samples are having the noise. There is the possibility of wrong prediction for the target value. Target value means output label, actual output label, right? More precisely, each training sample is pair of the features and actual output. That's what given here. You see the x1 for sample 1 feature 1 feature 2 and corresponding actual output label. Actual output label is represented with d. These are all represented with x, right? These are all represented with x. So the di is function of the all features plus error. When we are applying the model, when you are applying machine learning model, right? When you are giving the input for this machine learning model, when you are giving the input x, okay, first sample with all features, it will predict the output, that is called f of xi. That output may have error, output may have error. So this I is error corresponding to the ith sample. I is corresponding to the ith sample. So that's what given here. Then the task of learner is to predict the output with maximum likelihood hypothesis. That is maximum a posterior probability hypothesis, assuming all the hypotheses are equally probable. That means when we are finding the hypothesis for each sample, the model should give minimum error, with minimum error. So that is the aim of our model. So here the linear algorithm learns real valued function is depicted in this picture. The linear target function f corresponding to the solid line. You see the solid line, this line is indicating the uh, actual output. For our table is having the labels. Okay, our table is having the labels. This is the actual output. For this, yes, no, right? For this, we are uh, drawing the linear regression line. We are drawing the linear regression line. Then we are applying those inputs. So sample 1, sample 2, x1, x2, okay, sample 1, sample 2, like this. For this, we will calculate the predicted output, right? So predicted output will be calculated by model. So for example, here the model is predicted this is yes, this is also yes, but actually it is no. So this is predicted output. So for the predicted output for each sample, we are calculated by our model for each sample. That for that predicted outputs, we are drawing the line by using the linear function. So this dotted line is calculated for predicted outputs. You see there is slight difference. Okay, there is the slight difference in the predicted output and actual output line. Okay, actual output line. So this is the actual predicted output line. The red color line is predicted output line. So there is the small error. There is the small error available between. So this is the error. Okay, this is the error for this data point. So this is the error for this data point. Okay, so for each data point we are having the error. So this has to be reduced for forthcoming iterations. This may be iteration number 1, then iteration number 2. So like that we have to increase the iteration numbers. So here that error should be minimized. Error should be minimized. So when in which iteration you are getting less error, that will be your maximum likelihood hypothesis. So this is the way to calculate the hypothesis for linear regression algorithm for real valued function. The how this hypothesis minimize the squared error. As I told you, the in case of continuous variables, we cannot achieve this by assigning the finite probability to each of the infinite set of possible values. So instead of using the probability density function for continuous variables for such as error, use the integral of this probability density, right? So when you are applying the uh, integral for this probability density, we can achieve the minimum error. So here the lower case p refers the probability density function, right? So which is distinguish the finite probability capital P. So that's what given here. So when you are using this probability density function, uh, 1 by epsilon probability of x0 to less than or equal to x and less than x0 plus epsilon. Epsilon is the here error. Okay, this is the error because our data is added with noise. So here by applying this, we can reduce the error by keep on increasing the number of iterations. So this is the way to calculate maximum likelihood for linear functions. Thank you.